Hello everyone. We have a lot to cover today. We are going to focus basically on this little area and this little area. For those of you that don't know, well, I know you know, but Africa, Madagascar, North America, Greenland. I've actually been to Greenland 2 years ago to look at the failed Mesoproterozoic rift right in this area down here. Anyway, I digress. So I want to go over something first before I take a deep dive into this. We're going to be looking at several things today. First of all, I'm going to show you something about plate tectonics that you normally wouldn't get in the classroom, because especially at a beginner's level, because the plates form a pattern when they rift and move. Remember, the plates are rigid compared to the underlying mantle, although both are solids. Now I want you to look at, that's not it. Where is it? Stephen, here. This is from NOAA. I want you to look at this. It's hard to tell from maps in general. That's why I like to look at conical projections from the north or south usually, or global from, North America or Eurasia, whatever, because this doesn't give you the whole picture. Sure, this is cool because it shows you where the rifts are. The red is basically where the rifts are, and that's the youngest stuff. That's the youngest ocean crust. And you can see here, 280, but here you have purple, and it even goes deep purple. That's that place in the Mediterranean I told you is left over from pre-Pangea. But you go outside of there, and the oldest is about 170 million years old. So the crust, the ocean crust is young compared to the age of the planet, which is about 4.5 billion. Somebody asked me about the Caribbean here. That will be a later episode. But when you look at this, it gives you that good idea. Here's Hawaii, about the age of the ocean floor relative to other places. And like I said, I like this one. I think this one's from 2008. And it hasn't changed much because it's a nice faded color. It gives you the impression that this is a slow process. It's not rigid, jagged lines that make you think this might be faster. And over here, you might be like, whoa, we have really old ocean crust here, but we got brand new crust here. Steve, there's no rifting there. Well, there is. When you get subduction and you get island arcs like Japan forming, and technically, I guess you could count Korea, or not Korea. What is this peninsula called? Oh, I forget. But here's Korea. Sorry, I didn't mean to say that. Korea is there for different reasons. But you get like Japan, and you get Papua New Guinea and all these other ones here. You get back arc extension as these things move towards the continent. And the gray here is continental shelf. Now, some of this is gray and marked as continental shelf, but it's not. And we'll talk about that later. That's this Zealandia garbage down here. I have a bias, can't you tell? I don't have a bias against this. I have a bias against calling that a continent. Well, it's not really a bias. It actually is far rooted in legitimate complaint. Anyway, so you'll see occasionally red by island arcs. What happens is, as the plate goes under, because this is subduction here, it will not kind of lift it up, but kind of promote, like as one rigid plate dives under another, especially in ocean crust on ocean crust like here. What happens is the overriding ocean crust that's already over the plate inland more will tend to want to stretch. It's a hard way to put it, but if you put your hands together and your fingers and you start to push one side up, and eventually that other side's going to go down, and it's going to kind of lead the way, That's kind of what happens here. I don't have a good illustration of it. No one's ever done one. So I just want you to understand that's what happens there. Now, you look over here and you see some things, but I want to show you Scotes's stuff first. We don't need this. People are trying to sell this map and it's like it's completely public domain, but you know, whatever. That's coming later. So we're going to do from 750 million years ago to today. 750, you might be like, why not a billion? Why not the beginning of the Cambrian? Because 750 is a sort of unique number. And this is one of Chris's animations, because it is when the supercontinent Rodinia was pretty much breaking up. Now, I know you've all heard about Pangea, and you know that, but Earth had other supercontinents. Rodinia was one, and it's about 1 billion years ago to 750, not exactly. And we've actually are getting a good paleomag data from this to reconstruct it finally. And you may be like, well, Steve, if there's no ocean crust this old, how can you possibly reconstruct the continents? You can, young grasshopper, but that is a talk for another time. Okay, I don't want this to be too long. I want you to watch this. There we go. And like I said, this is Chris's. You can see up here. So he worked with. I got to give him credit, so I said I would. Here, you can read this. This animation just shows you the plate tectonic development in the past 750 million years. It's based on data from the ocean floor paleomagnetic poles. That's key. And then he has paleoclimatic and biogeographic information. So, but this is your driving. This is more important than anything else when you go pre-Pangea, quite honestly. It's paleomagnetic poles. I'm not even going to sugarcoat it. Oh, sorry. Thought I turned that down. All right, did you see that? Let's go back. These are names of proto-oceans and seaways. You look here, you can see Antarctica's all the way up here. Here's the equator, just like today. The equator has always been the equator. All right, it always has been. And you see Siberia's near there. You have Baltica. Now, this animation, I believe, is about 6 years old. And we've actually come a decent way since then, but it's still a good animation and still appropriate. What do you see here? You see a landmass over here and a landmass over there. Now remember, this would be a globe. So this is Siberia, but so is this little bit right here. So you can see the land masses are together. Now we actually know that Rodinia was not really, it had most of the land mass together like Pangea, but it was more like a glancing supercontinent. What do I mean by that? You would have things come in, connect, and just move away a lot more frequently than you did with Pangea. Because, you know, 750 million years ago, we did have active plate tectonics, but it has been changing since its initial planetary domination circa 2.5 billion years ago. All right, it does change. But this, let's walk. Notice the ocean floor is gray. Why is that? Because we don't have any ocean floor this old. The rifts are red, the subduction zones are blue, and that's based off the continent's paleomag data. You can kind of guess the subduction zones. The rifts are a complete guess. We don't really know. And you can see here, as you approach the Cambrian and you get into the late Neoproterozoic glaciations, the continents kind of just cluster around. They go from being mid-latitude, like with Pangea, when Rodinia was a thing, to being in one hemisphere. And what happens when we get things in one hemisphere like that? We get ice sheets, like today. So we're going to go to about the beginning of the Cambrian. Yeah, I think it's, got it, 541. And you can see now they came together briefly, but they're moving away. Now, a lot of us don't consider that a supercontinent, that 650 million year thing. Some people do. It was too short-lived. There's no, it's semantics as far as I'm concerned, really. We did officially define what a continent was back in 2021, and that doesn't fit the definition. But anyway, I digress. That is available for free on the Midwest Institute of Geosciences and Engineering's website, mige-web.org. So you can always look at that if you want. But anyway, you see you have these complex subduction zones here. We kind of have those today, but these two are conjecture. But the position of the continents are not. We know about the beginning of the Cambrian where everything was. And here's North America, here's the Great Lakes. We're closer to the South Pole than we are to the equator then. All right. Even today, now, some of the Great Lakes are closer to the North Pole than the equator, but not all of them. So here we move along. The Cambrian's coming around, it's doing its thing. You know, we're getting the late Cambrian, and we can see North America sideways, and we're getting closer to the equator, which is right here. And we're starting to get Cambrian transgressions and whatnot, but just keep watching. I'll try not to keep it too long. You start to see the continents are leaving that southern hemisphere. Now, they look real big here because of the way this projection is. Okay, but, you know, there's still a lot of landmass here. And here we're in the Silurian, and this is when we get massive reefs in North America. Okay, and if you notice, Greenland is here. Greenland's been hugging North America for a very long time. And then you get Europe slamming into North America. Well, part of Europe, Baltica, as we call it. And you get the assemblage, and here you get Pangaea forming. But look, he probably doesn't have the archipelagos on here, but even during Pangaea, we get its full formation around 300 million years ago. You're still going to see it move a little bit, but notice we still don't have any new ocean crust forming, okay? And we probably had a little bit. This is where the Mediterranean is, so there would be some here. But Pangaea is essentially forming now. Okay, and you see there's subduction everywhere, kind of crunching everything together, which means we have massive rifting here. But if you see this, at no point in Earth's history were all land masses connected. That's not a thing. Never have 100% of anything been connected. It's 80% or more is what we consider a supercontinent. And you probably have islands out here like you do today that are long gone, eroded to sea level or sea floor level, or got accreted or something ages ago. So you're going to see Pangaea still forming, but it's just kind of, you notice this is rifting away. So everything's not quite connected. All right. And we're still in Pangaea. And this is the part, here we go. Now we're here. This is essentially what most people think of when they think of Pangaea, is this shot right here, or close to this shot. All right, you can see we start to have something in the North Pole. Now we should have ice here. This is what, late Permian, early Triassic, around that time. And we didn't, probably like we didn't in Rodinia either. Why is that? Because even though we have Siberia, a good chunk of it up here, there's nothing in the South Pole, and we basically have one large ocean current. The continents aren't separated enough to really glaciate everything. Now, during the Ordovician, where was that? The Ordovician, somewhere around here. Where is it? 473. You can see it down there. You can see we have the continents kind of still nestled together. Now, during the Ordovician, there was not an Earth or a snowball Earth scenario. There never has been in the Phanerozoic. Nobody argues that, but there was glaciation. And then once again, during the beginning of the Carboniferous, once Pangaea first assembled in the southern hemisphere, you still have a lot of land, but now we're getting the land moving. And Siberia is going to change position fast enough to where there probably was an ice cap, but it wasn't very big. And plus, at the beginning of the Triassic, we had a great drying out, if you will. And now, I think, I forget what age we're in here. Jurassic, now look, you see the seafloor. New seafloor, about 180 million years ago. We're getting rifting. Pangaea's breaking up. Like breaking up, not just moving around the globe. And you see this over here. I find that very interesting too. So you start to see it. This is the Pacific Ocean forming new crust. This is going to end up being the oldest stuff in the Pacific Ocean. But you can see the rift is there. And and here's starting the Mid-Atlantic Rift, and this is rifting too. This is what we call a triple junction. That's how most rifts start, and they form like 3 prongs, and one will go extinct. And the other 2, that's in the extinct one's called an allocogen. But here we go a little more. We're moving along here. I'm just going to show you this because you all pretty much know this story. Now look what happens in Madagascar. It's attached to India here, but you go a little further back, and that thing's snugged on Africa. And here we have rifting drawn in here, but that doesn't seem to be the case. We do have new ocean crust, but actually it doesn't really look like rifting. It looks like there's a transform fault drawn here for some reason. But, you know, like here and here. But, you know, part of this is interpretive. You have to. See, and now you keep going, and now we're getting near the end of the Cretaceous. Dinosaurs are gone now. I missed it by 5 million years. It was 66 million. When the asteroid hit, and the asteroid hit right about here. All right. And you may be like, well, look at that subduction forming. Now, actually, let's go back. Okay, 93. You see this hits here. You get subduction here. Now, this subduction could have stayed there, and it did, but see how this broke? A new subduction zone formed, and this one's up here. That's what we kind of have going on over here, and I think that's what's going to happen in the future to North America, but talk for another time. Now watch it. Now we're at the age the dinosaurs went extinct. Here we have Chicxulub. Over here, it's actually more like here. It's not as big as the Caribbean, but you start to see multiple subduction zones forming, just like they do in the Pacific. They're just bigger in the Pacific. But here, let's just keep going. I'm just going to let this run, but watch Madagascar and watch how old that gets. And Greenland, I got to go back a little bit. I'm sorry. We go back to Greenland during the Cretaceous. I think it's right at the end of the Cretaceous. 91, 88, 79. I'm going to try to get it there. You see, the rift moves up here, but that's going to change. Now, during this time, scientists do think Iceland, the hotspot, started. Okay? And started under Greenland. We know that from not paleomagnetic data. What do you call it? Geomagnetic data, geophysical data. There are videos about this part out there. Nobody talks about the west edge, but there is rifting there. Greenland just kind of sort of as a hotspot moved. The rift moved from here to over here where the hotspot was. And that's why I think that's going to happen with Yellowstone over here. That's where I got the idea from. Iceland is helping me with a lot of things, actually. Now you look and you see you still get rifting here. Madagascar is just kind of floating ever since it left India. It's not accreting to Africa. And it does look like it kind of fits in there because it did. And now we're just going to go backwards, so I'm not going to show you that. All right. So we did that. I want to show you. No, we're not going to show you that yet. All right, let's show you what happened with Iceland. And I am going to turn the volume up on this one so you can hear it. Actually, no, I'm not, because you can read it. Okay, they're going to talk about this track of the hot spot under Iceland here. All right. They're just giving you the background. I've been to Iceland too. So here we have the hot spot. I want you to look at that. This is a block diagram. This would be your crust, ocean crust. This would be your lithosphere. And here's your hot spot, catching up on the lithosphere. Whether or not this is an accurate model, I don't know, but it's good enough. And they're just showing it and rotating it for you. And here's the hot spot beneath neighboring Greenland. You see that? And here they're going to show you. This is a recent discovery. This is since Chris's video. This is relatively new. You see this track here? See how this isn't colored red because it's warmer. It's colored red because of the geophysical data. See the heat flux? warmer. I guess I can say it is. I guess I can say it is because it's warmer. But see, it's also red here. Heat flux doesn't exactly mean this part of the continent's warmer. Talk for another time, but we'll talk about it like it is, all right? So you see gravity data 2, and this is exaggerated. When people show you this, this is not what Earth looks like from space. This is called, vertical exaggeration. We do it all the time to draw our eye to features that if they were to scale, we wouldn't even see. That's why this is like this. This doesn't mean Earth is shaped like that. So they're going to talk about Greenland and his little ice sheet, and the thermal track was the continent over geologic time. And here we go with 100 million years ago, the Iceland hotspot. And then Greenland kind of just does this number with North America until North America starts breaking away during the Cretaceous. And if you look at that, it starts breaking away. Let's go back. So let's get it to about 70. Okay, so this is when we start getting rifting here. See, the hot spot's under Greenland, so it's going to favor rifting here until about 50 million years ago when the hot spot moves off. 40 million years ago, it's now off of Greenland. So this rift is no longer being favored. The Mid-Atlantic Rift decided to follow to the hot spot on the east side of Greenland. And that's basically what we see going on today. Now, Greenland and Iceland will eventually come together. The Atlantic Ocean will close. That's called the Wilson cycle. But here we got this here. This also helped me figure out something interesting about part of North America 1.85 billion years ago. See, it says warm bedrock. Just go with it. It's fine. But like I said, the thermal flux is not exactly that. That's not exactly what it means. And I do love this animation of the rift. But you see the big continent rift here. And these are subduction zones over here. And this is the rift. You see the rift dead ends up here. It doesn't continue. And you might think that's odd, but it actually isn't. It makes total sense. But I think I'm going to save that one for a different episode because we're already past 20 minutes. So I'm just going to go over a couple of things here, and we'll do another episode shortly. So when you look here, what you see, and in our paper about definition of continents, Greenland happens to come out as a continent. It fits our definition. It just happened that way. So this is new ocean crust. Okay, and now this is new ocean crust. So this is where the rift used to come, but decided it wanted to go over here once Greenland moved off the hot spot. And here too, you see the Mid-Atlantic Ridge, and it kind of terminates right here. As you can see, where's the North Pole? 88, 77. I don't know if I'll be able to find it. But right at about the North Pole, as I'm going to say, there's no land. Okay, there's no land at the North Pole. It's all ocean crust. Now here we have what's called the continental sea or inland sea between the Scandinavian countries and mainland Europe. This will eventually go away. It will close. And here's the Mediterranean, but you see the Mediterranean's ocean crust, and this is where the oldest is, somewhere over here. So that's the leftover, and this is a rift for another time. But we come down here, and you see Madagascar. I can't find anything on. There are papers about this, by the way, and the conclusion is, and the consensus is, still, we're not sure what's happening. But you see the rift here, and you saw Madagascar rift from India, and it just kind of stayed there, and Africa kind of moved away from it, with no true actual rift forming here. What this is, remember I told you about back island arc extension? That's probably what happened here, except what happened is you didn't get any rift. You didn't get too much new crust forming, maybe in the beginning. What happened here is more of a stretching of the crust, not which it is in the back of an island arc, but it's not it's not the same thing, because there you'll actually get an actual rift forming most of the time, and you'll get new lavas in with the sediments. But here that doesn't seem to happen. Now this might be an archaic way of plate tectonics moving. This might have been more common, say, 2 billion years ago than it is today. We have other archaic forms. I think hotspots are a leftover from our old tectonic system. And in our next video, there's another thing that I'm going to show you a clip from a guy whose channel is far more popular than mine, but he really needs to stick to space because he sucks at geology. Well, I shouldn't say sucks. He has a good channel. I'm not going to give his name away here, but it just, he's young. All right, let's say that. He doesn't suck. It's incorrect. He's young. He doesn't know a lot of things. He just looks in the recent literature, grabs it from the media headlines, and he does do in-depth discussion on it. He is scientifically literate, and that's good. But you can tell he's much more of an astronomy guy than a geology guy. And we're going to talk about that in the next video, I believe, as well. So I just wanted to let you guys know. I think that's it. If you have any questions or comments, please leave them below, and I hope you learned something.